Today I'm gonna give you the proof of the Rodin-Sullivan's theorem on the rigidity of hexagonal circle packing, and then I will tell you some questions. So mainly it's sort of I like to tell you some open problems in the area. So first, I also like to show you some slides. So first, let me recall that the proof. So our new proof depends on this Doyle's theorem, which I show at the beginning of in our first lecture as the example of a flat structure. And so I'm going to fix today the standard triangulation is the standard hexagonal triangulation with a complex plane. It's an infinite triangulation where every triangle is regular of size 1. Okay, so that's this extended. But we think of that as a topological. Okay, so this is a topological, it's a pretty short triangulation of a simply connected space, and it's a vertices. I'm going to use V is the standard hexagonal lattice. So this is a standard. So if we put these three things together, take the complex plane, take the standard triangulation, and make every length of the edge 1. That's the standard geometric triangulation of the complex plane. And so we think of that as a flat piecewise linear surface. Okay, so this is the standard space. And now Doyle's observation was you assigned every you write down any linear function on the lattice. This is just to take any non-constant linear function defined in the complex in the plane and restricted to the lattice, and you take e to the takes the exponential of this function, and that will be a assignment to every vertex you assigned a positive number. Think of that as a radii, and this circle packing metric is always flat. Okay, so that's the first which we verified, and the second of all, as I always mention, it's a spiral. It's a spiral circle packing, and one consequence of that is that so this is now a metric space. It's a simply connected space with a metric whose curvature is equal to 0. It's a flat metric, but this metric space is not isometric as a metric space. Is not isometric to any open set in a complex plane. Okay, so let me show you the picture, and this is one of the key steps in the proof of the Rodin-Sullivan. So here is if you Google the Doyle spiral, you see this is what I downloaded from the web page. Okay, so that's what's actually happened. You choose some non-constant linear functions. You see this is a circle. It's going to tangent to 6 others, and you try to isometrically immerse this flat metric into the complex plane, because this is still simply connected. There's always immersion. And what you see is that there will be lots of self-overlap. And so this is one layer, and there will be some other circles behind it and above it. And so in fact, it's a spiral. Okay, so this, in fact, is Doyle's proposed. So the isometric immersion is Doyle's proposed approach to the exponential function using circle packings. And let me show you a few more. So if you Google it and this is the corresponding picture that we use for spiral hexagonal triangulations. And so this is now the case where we take any linear function again, we raise it to the power. So is this in the Doyle's case, the length of an edge is equal to the sum. So this is now a radius function, and you see this picture. And now if you, in a discrete conformal case, the length is going to be the multiplication. So okay, so in that case, I call this conformal factor. You just multiply these together, and again, it's always flat. and you see the same picture. It's going to self-overlap. And so every vertex has degree 6, and individually each of that is discrete conformal to the standard hexagonal triangulation, and it's going to overlap. And this is what we are using to prove the analog of the Rodin-Sullivan in our case. So let me show you one more picture. So these are the two spiral. These are the Doyle's case, and you may be surprised to see these are the people. So now some artist who's getting very interested in these designs, and so they choose this function. This function is ax plus by. Choose this a and b really, really carefully, and you see this picture. So you may be surprised that there are no self-overlap. And so what's going on? I'll let you think about it. Okay. So is this a contradiction to? So the Doyle statement is that no matter how as long as your function is non-constant, there will be two circles in the original circle packing. Okay, so this is the original sort of combinatorics circle packing, and now you have these strange flat structures, and you immerse that into the plane, then you can find the two circles whose images are going to overlap, but you don't see the overlapping here. Okay, so it's a perfect picture. And so is this a contradiction? I'll let you think about it. Okay, so these are the very specially chosen A and B are say A divided by B is the rationals and things like that. And here is a picture of 3D scanned. So I'm going to show you a 3D picture. So this is a 3D scanned human face, and these are the scanning produces a set of points, and then they produce the triangulations. And in general, the triangulation that you started with, maybe it's too small. You see a lot of, for instance, you see a lot of triangulations which is not Delaunay. So these angles, the two facing angles, is really both of them are bigger than pi, and lots of software now. So these data is no good for processing. It's going to create a lot of errors, and you turn that into Delaunay. Okay, so this is what we're going to actually do to starting the discrete conformal processing. So the set of points are the same, but you do these flips and producing Delaunay triangulations as the first step. And now let me also show you. This is a standard picture for the Andreev-Koebe-Thurston theorem. So this is part of the Thurston's conjecture. You draw this Jordan domain, and you approximate that by regular hexagonal triangulation. This dot here, the dot point is a base point. You take a simply connected domain, take a point there, and that point by the Riemann mapping is going to send it to the center of the unit disk. And so this is the marking point, and you map it by Andreev-Koebe-Thurston. So what does this picture shows that this is a very good approximation to the Riemann mapping theorems. And you may see there are some accumulations here which really corresponds to the region where the curvature is large. Okay. And that's our picture. So you take a Jordan domain and you take 3 points on the boundary, and then the Riemann mapping will say there is a unique homeomorphism from the closed Jordan domain to the regular triangle, which is conformal in the interior, and send these 3 points to the 3 vertices. And we now approximate this by regular equilateral triangulations. And so you just take 1/n size and put this largest simply connected region inside it, and take 3 points close to these. And then we run the discrete conformal process to produce this map. And as I mentioned, this process is more complicated and difficult than the circle packing, because the discrete conformal process is going to change the triangulations. And you can see that here. For instance, this vertex now is the interior, but it has degree 7. Okay, so so for the vertices inside, it's always degree 6. It's okay, but for vertices here, this is a degree. This is okay, but this is a degree 7. So it's due to the flip operations, and because of that, this is really much more complicated to prove so there is no. In the Thurston's case, it will produce a piecewise linear map from the circle packing in the domain to the circle packing in the target because they have the same combinatorics. Just send the center of the circle to the corresponding center and then extend linearly to the triangulation. But here now we don't have a triangulations because the triangulation is changing, except these vertices remains. And what we observed before we proved the convergence was that if you subdivide this picture finer and finer, and you take a compact set in this inside region, take a compact set here, and you look at this finer and finer subdivisions, those triangles, the subdivision which intersect the given compact set, and the combinatorics is not changing. And so you see here, the stuff near the center is always regular. So you keep subdividing it. In the end, these triangulations really converge to the regular triangulation, and that's conformality. So that's what we proved. But what we prove at the moment is I can choose a very special choice, a very specially selected approximation, and this is converge. Okay. Otherwise, because of this flip operation, it's going to create some troubles. Okay, so that's that. And now let me also show you the software we produce for 3D. So this is a 3D scanned human face. And so nowadays, you can now really print it out. It's a 3D status of a person. And what they do is take, at the moment, this is a quite precise process. So you take the best these 3D cameras is a laser. They shoot the laser to the human face and select a lot of points. This is every point has a 3-dimensional coordinates. And then, so here is the actual triangulation you see. This is so selecting a point and then you do the Delaunay. So this is after the process. These are the Delaunay triangulations. And now we use our discrete process to turn that into a conformal map. So this we can now prove this is an actual image of that face. So there is a one-to-one map to this region preserving angle. So this is an accurate picture. Okay, so and you can see the triangulations here too. So that's the actual triangulations. So this picture is produced by David Gu. Okay, so that's what I want to show you, and now I'm going to prove to you that this is it proves that this is really a real approximation. Okay, so let me just stop this. Oops. Okay. Okay, so the goal here is to prove Rodin-Sullivan's theorem. Oh, by the way, there is also, as I mentioned, there is really a much faster algorithm based on circle packings. It's much more robust than us because you don't have to do the triangulation change. The triangulation change that when it run into a critical Delaunay, you need to do the diagonal switch. That takes a lot of computational power. But the drawback of the circle packing is that it works really well for planar regions. you have this canonical. But if you have a 3D scanned human face, this is a really a curved, so a non-flat surface now. And then circle packing is not working well because in general, the 3D scanned polyhedral surface, you cannot produce a number at the vertices whose length is given by the sum. Okay, so most of the polyhedral surface that you produced from the 3D scan cannot be packed by circle packing. If you can pack it, if it happens to be the case, then Thurston's algorithm is really fast. It will produce a much faster algorithm. But at the moment, it works really well, say, in the planar regions, not for the curved space. And so in some senses, the circle packing in some senses more like Riemann mapping. And the discrete conformal is a discrete conformal for Riemannian metrics. OK, so let me state Rodin-Sullivan again. So this is the key step in showing that the limit of the circle packing map is a conformal map. So the statement is, again, I'm going to use the same framework. T standard is a hexagonal triangulation of the plane, and V is a vertices. So it says that suppose R is a radius assignment. You assigned every regular point in the regular hexagonal lattice a positive number. Think of that as a lattice, such that the complex plane with this topological triangulation and this R is a flat circle packing metric. So assuming that we can now produce a flat circle packing metric, CP stands for circle packing, and we know by Doyle you cannot conclude this R is a constant right away because of this. So assuming that it's a metric which is isometric to an open set in the complex plane. Okay, so geometrically, what's really going on is that you take an open set in the complex plane, and we start doing circle packing on it. Okay, so this open set now has a hexagonal circle packing. You keep going like that. And without self-overlap. And so the triangles near the boundaries could have a small, very small diameters and so on. But every circle is tangent to 6 others, and the whole open set is a union of these disks and these triangles bounded by the disks. And suppose you see this picture, then the only way you can do it is the regular. So. Okay, so that's Rodin-Sullivan theorem. I'm going to give a proof today. And the analog theorem that we need for the convergence is just replace this. And so suppose say lambda is a discrete conformal factor such that you take the complex plane, take the standard triangulation, and now you take the standard hexagonal triangulation. So I take the standard one and stretch it by lambda. So this is a discrete conformal vertex scaling part such that this guy is a flat Delaunay triangulation, which is isometric to an open set in the complex plane, then this lambda has to be a constant. Okay, so that's the analog theorems. In fact, I also conjecture that you probably don't need a Delaunay. That may well be true as well, but I don't know how to prove it. So Delaunay is essential for us to prove it because of the maximum principle. If we don't have Delaunay, the maximum principle is false, and we can't do it. But it's highly possible that this condition is not needed even. Okay, so let's prove it. So I'm going to tell you how, in quite detail, how this theorem is proved, and then this theorem, the proof here is more complicated because of the degenerations. I will indicate. So what's really going on? So we produce a proof of this, and then we realize the proof also works here. So I'm going to tell you the proof, which really is simpler, what's going on here, and I will indicate what's the corresponding part. Yeah, that's exactly this picture now, because it's a constant one. Okay, so let's prove it. So maybe I'm going to call this theorem 1, theorem 2. So let's prove theorem 1. Let's make a modification. Well, we always do that. Radius parameter is not the best to change it, and so let's let u to be the function on the vertices defined by u at a vertex is equal to log. Okay, so I'm going to write this radii assignment is really e to the u. It's the u function composed with exponential function. And now we have this ratio lemma, which we proved last time. The ratio lemma says that if you have this circle packing appears here, the ratio of any two radii, adjacent radii, is at most 100. So if you take log, you will get u of I minus u of j is the most log of 100 for ij in V and adjacent. So if you have two adjacent vertices, then the difference between the two values is the most log 100. And therefore, this tells you that if you take any two points, so this is the standard hexagonal lattice. And you take I here and j here, then you can compute their combinatorial distance. So in this case, the distance 4, and you will have the less than or equal to the combinatorial distance between I and j of log 100. So for any I and j in V, and this is the combinatorial distance between the two vertices. Okay, so that's the first consequence of the say it again.
R is different from lambda.
Lambda.
In the theorem there's a lambda.
Sorry. So I just I probably should call lambda. I just shifted to u. Is that so? I call this u. Okay. Okay. So that's that. And now what we want to prove is really this u is a constant, and so the difference will be 0. Okay, so let's assume u is not constant now. So assume I'm going to derive a contradiction now. Assume u is not a constant, and I like to prove derive a contradiction. Okay, so So what can we say then is this V is generated by, as a group, is generated by two vectors, right? So V is generated by 1 and eta, which is e to the pi I over 3. And we have a function defined on this abelian group. And so I can, it's a non-constant function, so I can say there is a delta which is equal to either to one of the generator, 1 or eta, such that the difference, so such that if you look at the difference of u, say j plus delta minus u of j, this guy for v running over R for vertices is not equal to 0. Okay, so in one of the direction you move, it's not, it's non-constant, and so in one of this is not 0. Okay, so then I can find a sequence. So you can find a sequence of vertices in V such that the value u of Vn plus delta u of Vn is now at least lambda minus 1 over n. And so I choose a sequence of vertices whose difference is now approaching to the supremum. Okay, so we can always do that. And maybe let me illustrate what's going on next. So we're going to take some sort of Gromov-Hausdorff limit and produce another patterns, and we're going to choose really take a double limit, and we're going to get to the Doyle's case. So let me just before I go on, there will be some formulas. Let me just illustrate what's really going on. So in this circle packing now. Let's say I'm going to just draw the picture of, say, delta equals 1. Okay, so what you see is that you have this, the lattice is now just focused on the horizontal z inside the V. And we see it's a non-constant function. The function is non-constant in this strip. And the ratio, the difference is by the way, this lambda is a finite number, right? Because of the first fact, the ratio lemma. So lambda is a finite number. That's important here. And we see these pictures now. Right? This is supposed to be the corresponding circles. So I'm going to choose some Vn where the adjacent ratio is approaching to the maximum. The adjacent ratio of the radii is approaching to the maximum ratio along this strip. And but this V is a lattice. And so what I'm going to do is, so this is my, say, the original vertex. This is the origin. And now I'm shifting. What I'm going to do is I'm going to shifting this circle packing with original is V here. I will make Vn to be the center. And also I'm going to do a rescaling so that the radius of the new circle packing, just grab this one, do a translation to it here, so that the radii is going to be 1. So we can always do that. This is just a normalization process. And so that's what we're going to do. So let's define a new circle packing metric, Un, just by what I'm doing here. I'm going to do a shifting of the base point, and then I'm going to do a rescaling, but in terms of the log radius. Okay, so if you think about it, this will be Unj is going to be U of j plus Vn. And that's a shifting. Okay, so this is the original circle packing. U is the original circle packing. If there are no Vn, that's the original circle packing. And now because this is a a group here. I just shift the origin to Vn. And now I also do a renormalization to make the radius to be 1. And so it's U of Vn. So this is now a new function obtained by shifting the base point and rescaling. And so clearly the circle packing metric e to the un is again flat because the original one is flat. It's just shifting the base point. And it's really the same as a previous one, right? And what do we have here? And now you have un at the origin is equal to 0. So this circle packing metric at the origin has un to be 0, and so the radius, which is e to that, is 1 now. It's normalized. That's what's going on. And now if you look at this un, this new shifted circle packing metric, and let's see what does it have. I have this, right? Un and 0 equals 0. And un delta minus un 0. So it's now just these two neighbors now is at least a lambda minus 1 over n. That's a definition, right? This is just this equation. Just do a shiftings, and that becomes that. And un j plus delta minus un j is at most lambda. That's again the definition. So the adjacent, the ratio adjacent radii is at most lambda because I choose lambda to be the supremum values. And finally, we also have the last one. So you can un of j is at most, well, this is equal to un of j minus un of 0 because this is equal to 0. So it's less or equal to the distance from j to 0 times log 100. Okay, so what do I have? I have a sequence of I have now a sequence of vectors in R to the sequence of functions defined on this countable set V, normalized at 0 to be 1, and these two is obvious, and that. So this condition tells you we can now using Cantor diagonal process, right? So we can now find a convergent subsequence. So this tells you that exists a convergent subsequence. Say just say itself. Say un itself, which is going to converge to u infinity in the weak topology. This is really the Cantor diagonal process, right? So we choose a subsequence where the subsequence at 0 this is a convergent, and now you can choose a subsequence which is convergent at delta, right? The delta is just marched to one direction. It's bounded, and then you keep going. So you go to the next one. This tells you it's bounded, and keep going. So we can find a convergent subsequence in the product topology such that un this function at j is equal to the limit as n goes to infinity of un j for every vertex. So this is the compactness argument because of this estimate. And so the ratio lemma really controls the convergence. And now let's take a look at this new. This is in geometry, what we are doing is I'm gonna look at these adjacent vertices whose ratio of radii approaching the supremum, and shift it to the origin, and renormalize, scale it to have radius 1, and we're going to take a limit. Okay, so and you can do the limit because of the ratio lemma. So it's going to come. So we're going to produce a. This will give me a new circle packing metric, e to the u infinity, which is flat. which is again flat because the original one is flat. So the reason is, of course, the flatness is about the curvature. The curvature is a function. Curvature is built out of these angles, and the angle is a continuous function of the length, and the length is now a function of these u's. And so as these u's, as this ui, the radii converges, and therefore the length converges, and therefore the angle converges. And the angle now summed to be 2 pi as a continuous function, and so it's still flat. But we may lose some of the information. But this is a flat. Circle packing metric. And let's take a look at what's the property does it have. Well, we have these two properties, and you take the limit, we get u infinity of delta minus u infinity of 0 is going to be equal to lambda, well, bigger than or equal to lambda, and this is u infinity j plus delta minus u infinity of j is less than or equal to delta for all lambda, for all j. And that means this has to be equal because this is true for any of them, and it's achieving a maximum point. So this tells you that this function f of j equals u infinity j plus delta minus u infinity j has a maximum point at 0. And so this guy is, we know it's a flat circle packing metric, and this is now by again shifting base point to delta. So this guy is flat, and this is obtained from the flat by shifting. So this is again flat. And therefore, Thurston's maximum principle tells you that it's impossible unless it's a constant. So Thurston has to be a constant function. So what do we have now is, after you choose this limit, this function is always equal to lambda for all j in the vertex. Okay, so that's good. And knowing this, we can now repeat the same process. And so during this process, we really didn't use too much information. It's just that you give me any flat circle packing metric. I can now, using the ratio lemma, I can choose this point approaching this max supremum ratios and do the same thing. And so let's repeat. So let's let delta prime to be the remaining. So these two are the generators for the lattice, and we choose one of them, delta, so that this guy, the supremum, is non-constant. And take the remaining one and repeat the same thing for now for this function. Okay, so then we can select another sequence of the subsequences. So I now produce a new function which is infinity through infinity. And this function now obviously has that property because of the point-wide convergence. So this function satisfies u j plus delta. J is equal to lambda for all j. And for the second generator, I can make that constant. This constant may be 0. Is a constant for all j. Okay, so that's the second selection process. And that tells you that this function is a linear function because you move in one generator direction, it adds by a constant, and another one by another constant. And it's a non-zero, it's a non-constant it's a linear function, but it's not a constant. So this is how we choose it. And therefore, what we have then is we have a Doyle situation. So U hat from V to R is linear, and e to the U hat is a Doyle spiral circle packing. Okay, now that's impossible. This is gonna be contradicting to the condition that the metric is isometric to an open set in the complex plane. So the point now, so the Doyle theorem will say so you can find the two circles. So C1, C2, it's a distinct circles whose isometric immersion image in C overlap. So abstractly, I guess I show you. So this is sort of the abstract circle packing metric of different size on this space, and we now isometrically immersed this. This is really the development map into the complex plane, and that's these spiral pictures we see here. Okay, so you can now find the two circles, distinct circles, whose image overlap. But this, how do we get these circle packing metrics? This is obtained by taking limit. So U infinity, the U hat is really obtained by taking limit of this U hat is U infinity, taking this circle packing by doing some shifting of the base point and rescaling and take limit. And so if this limit process will say, if this occurs, if we have two open circles whose images is overlapping, then star holds for before the limit, okay, because it's open set overlapping process, and this convergence is really it's a uniformly or compact convergence. And now you repeat, and so this circle packing, flat circle packing, sends two circles to two circles with overlapping images, and so this repeat this process. This holds for e to the u, for the original one. Okay, and that's impossible because that's what we assumed, that this guy, for this guy, the development map is in fact the embedding. Okay, and so that's how we proved it. And proof for this case, for our case, it's basically follow the same steps, but it's a little bit more complicated. Because we have the same ratio lemma, but when you take the limit, we run into some troubles here, because in a circle packing case, I give you these functions. These functions you have these circles now, which is the radius is equal to the e to the u, say infinity of some vertex, which is always positive number. And the triangles is the actual triangle. Now, in the vertex scaling case, the triangle may degenerate. So theta could be equal to 0. Okay, so still a positive number, but the triangular inequality, when you take limit, may become equality. And then these degenerations really creates a lot of pain. And so, so I mentioned here, so here is the Thurston's maximum principle for circle packing. There's no degenerations I stated the maximum principle yesterday for the non-degenerated case, but we really need to work hard to work out there is a maximum principle even for degenerated triangles. And so that's a painful part, but in the end it works out. And so that's how this is proved. Okay, so that's the proof. And now in the rest of the 40 minutes or so, I'd like to tell you some questions. So let me tell you, I think there are some really interesting problems I personally like to know. So, and we also see the relationship between this theorem and many of the classical geometries. And so it's good to know that this is not just an isolated computational geometry problem. It has a lot to do with classical geometries. So let's consider this theorem too in a special case. So special case of theorem 2, where the special case we have now, suppose you have a C, a standard triangulation, and a vertex scaling of the standard one. And let me assume that this is a geometric triangulation. Of the complex plane. Okay, so in other words, the statement here, which is isometric to open set, the open set is a whole complex plane itself. And so what's going on now? So here we have the standard regular triangulation. And now here I have a geometric triangulation of the complex plane. So every point in the plane appears here. Okay, so these two differ by a vertex scaling. So the vertex scaling you can now phrase it in terms of the cross ratio. And so here is this is a Delaunay. Okay, it's a Delaunay triangulation of the complex plane. Subject to the condition, the discrete conformal here. Now this vertex scaling really says that I have a Delaunay triangulation of the complex plane, so that whenever I take an edge here, you look at the four sides of the quadrilateral containing E, then the cross ratio is equal to BD. Okay, so this condition is true at every edge, and the theorem says that if this occurs, then if this condition is true for every edge, and then all the edges have the same length. And now let's take a look at, okay, so what I'm headed for? Let me maybe, before I move to the next, I really want to know what is the non-compact case. So the motivation is this question. So yeah, let me pause a little bit. So here is a question. So what is the discrete uniformization for non-compact simply connected polyhedral surfaces? And because, as I mentioned before, the uniformization theorem for Riemann surfaces is really reduces to the simply connected case, namely two-sphere or the planes and the disk. Okay, so you prove that it works for all. And so, but the definition I give for discrete conformal only works for compact, because it's a finite process. There's only a finite number of triangulations. If there's an infinite number of them, what should be the statement? What's the statement of it? And so I like to motivate this by looking at this example. So here, this set, now it's all in geometry, as a vertex set is V. So this is a vertex set. And now this triangulation, let's say, has a vertex set, say V1. Okay, so V1 is the physical locations of this. And then from this V1, you do the Delaunay triangulation that produces the structure. And now from V1, so V1, you think of that as a point in the complex plane. And we're going to go to hyperbolic geometry, as you can see. This is a C. This is a C. And so here I have this regular hexagonal lattice point. And here I may have some irregular. Okay, so, but in the end, it's not, right? But we don't know at the beginning. So the statement, you take a discrete set in the complex plane, and this is a standard one. Let's do the convex hull. So you take the convex hull of this V in hyperbolic space and look at the boundary. And here you do the same thing. You look at the boundary of the convex hull in hyperbolic space of this set. So as we saw before, this condition tells you that these two convex hulls surfaces isometric. And so this is a convex hull, which it's kind of pretty picture. You see over every triangle, you have this ideal, unique regular ideal over it. And so that's this convex set here. So so the CHV so the convex hull itself is above it. Okay, so the boundary is this tiny small bubbles here, and you have the same thing here. So I couldn't do it. So what does this theorem says in this case? Well, it says if there is a isometry, so suppose that's this condition, discrete conformal. So so if there exists an isometry H from the boundary of the convex hull of the standard hexagonal lattice to the boundary of the convex hull, of the other one. But we have these triangulations here, so I need to assume that this is isometry between the two, preserving the cell structure. So it has two-dimensional faces. These faces are these triangles, and here I have this hexagonal information I need to. So preserving cell structures, and then the so this is a translation of the condition that it's discrete conformal. Then these two differ by just the scaling. So then and then the convex body is isometric too. Okay, and for those who, you see, this is really a classical problem, right? This is a Cauchy type problems. And so this is Cauchy's rigidity. This is the famous, probably the first rigidity theorems in geometry. It states following. So if P and Q are compact, convex polytopes in three-dimensional space such that you can find an isometry H from the boundary of the convex body to the boundary of the convex body, preserving the cell structures. So that was Cauchy's original condition. Then these two differ by a rigid motion. Okay, so the convex bodies are rigid. It's determined by the geometry of its boundary. And we are really headed, this theorem is really going toward that direction, except we are now in the non-compact situation in hyperbolic spaces. And let me say a little bit more. So there is this work by Alexandrov. This is the beginning of the Alexandrov school, geometry. So what I'm really headed for is that as you can see, this question is really a counterpart of the Alexandrov-Cauchy type of problem in the new setting. So Alexandrov theorem is the following. If you look at the boundary of a convex polytope, it's going to be a polyhedral surface of positive curvature, as we saw before. So P convex implies boundary P is a PL surface on the two-sphere with some vertices and the metric of curvature bigger than or equal to 0. It's a convexity tells you that. And his theorem says the other way around is true. So the theorem says that if I have a PL metric on the two-sphere with a finite set of points of curvature bigger than or equal to 0, then you can find a convex polytope which is isometric to it. So this is really isometric embedding problem. So then exists a compact convex polytope P whose boundary is isometric to D. Okay. And in fact, there is another amazing theorem by Pogorelov. So this condition of Cauchy, here, just like what we have here, is a consequence of an isometry. You can remove that. So Pogorelov proved this amazing theorem. Pogorelov was a student of Alexandrov. So if P and Q are two compact convex bodies, so it may not be a convex polytope. It's a convex hull of any compact set in the three-dimensional space, such that the boundary of P in its intrinsic metric is isometric to the boundary of Q, and then they differ by a rigid motion. And I should also say that Alexandrov really first proved these theorems, and then he proved that you can really replace the PL metric by any path metric on the two-sphere, and he defined the curvature for the path metric to be bigger than or equal to 0, and then there exists a compact convex bodies whose boundary is equal to that. And so it's an extremely general program. Okay, good. So from this point of view, here is a proposed approach to this question. So the picture is something like we have a polyhedral surface which is simply connected with an infinite number of triangulations, and the uniformization in the classical case will say this guy is going to be conformal to C or D. And it's now difficult to define the discrete conformal. So I may as well just go to the hyperbolic space. So this will be something like so what I'm going to do is just that you see a Euclidean triangle I replaced by this ideal hyperbolic triangle and glue them together. And you will produce a hyperbolic metric on a punctured surface, right? So this is, I give you a complete hyperbolic metric D on either the complex plane minus V or the unit disk minus a set. And so V is a discrete set. And the discrete uniformization should predict that this guy, so somehow we can now make this flattened. This should be isometric to the boundary of a convex set. So isometric to the boundary of a convex set in V prime if you have C minus V. So if your surface is a hyperbolic metric on the conformal structure here, it's going to be, you can produce a discrete set in a complex plane, and you take the convex hull of this discrete set, and this metric should be isometric to the boundary of this, and V prime is unique up to Möbius transformation. So this is really part of the Alexandrov-Pogorelov's picture. And now if you have a D minus V, what are you going to do? It should be isometric to the boundary of, so this V is now a discrete set in an open set, in an open disk. It should be isometric to the boundary of a convex hull of V prime union the complement of D. Okay, so that should be the, I don't know how to prove it. That should be the discrete uniformization theorem for polyhedral surfaces. The way to look at it is really to phrase it in terms of hyperbolic geometry. Okay? And that's sort of the Alexandrov-Pogorelov type result. So let me say a little bit more about it. Now, before doing that, let me also tell you Thurston's. Oops. There is a Thurston's observation. So I will say a little bit more about this. But before doing that, there is this work by Thurston. This is in his chapter 8. If you look at the notes, the first paragraph of 8.1 to page 185, and his proof is really interesting. You read the proof. So let me tell you what the theorem is. The theorem is relatively simple. So the theorem says that take any closed set X in the Riemann sphere. Now you can take the convex hull of the closed set in the hyperbolic three-dimensional space. This is a convex set, and you look at the boundary of that. So this will be some surface. It's a convex surface. And the Thurston theorem says that this is a complete hyperbolic surface in its intrinsic geometry, in the intrinsic path metric. Okay, the proof is in some sense is not too difficult because if you think about how to take the convex, let me say, so his proof is really interesting. It's a physics. Read the first paragraph. He said, think of this as an object in three-dimensional space. You just roll it in the planes and you see it's hyperbolic, and that's what he says. And if you really want to see the precise proof, it's in Epstein, Marden wrote an excellent paper exploring the geometry of the boundary of convex hull. So the boundary is the convex. So here, what's important here is this X appears at infinity of the hyperbolic space. And so if you think of the hyperbolic space as the boundary of a convex, as the interior of a open ball, what you're doing is you take some closed subset here, and you start doing the convex hull by drawing hyperbolic geodesics between these, right? Really, you take all possible hyperbolic tetrahedra whose vertices inside and look at the union. And that's this convex hull. And from this point of view, you see every point in the boundary of the convex hull. So you take a point in the boundary of the convex hull, then it lies in a geodesic. So P lies in a open geodesic segment, which is inside the boundary. Okay, so this is a very special because we are taking convex hull of set at infinity. And that tells you that this surface is a rule surface. Okay, so every point in your surface, there is a geodesic goes through the point and still lies in the surface. And if it's a rule surface, and then say in the Euclidean case, maybe it's easier to see that in the Euclidean space, a rule surface tells you the Gaussian curvature has to be non-positive. But it's also convex, so the Gaussian curvature is not negative, and so therefore the Gaussian curvature is 0, it's flat. And the same argument works in hyperbolic space. And so on one side, because you are taking convex hull at infinity, the curvature now is less than or equal to -1. But convexity tells you the curvature is bigger than or equal to -1, so it's equal to -1. So that's what Thurston proved. And this is really very interesting because this is now I'm gonna sort of upgrade this question to a higher level in some sense. So I was quite excited about this relation, and I talked to Mike Friedman, who was my advisor. So I said there could be some relation between these two, and then he immediately reminds me of the curve conjecture. So let me go to a different aspect. So this is a curve conjecture. And I want to relate all of these together. So here is a theorem of curve. It's about Riemann surface. So what we are doing here is a hyperbolic metric. And the Riemann surface and hyperbolic metric are closely related by the uniformization theorem. So here is Curve theorem. Maybe I'll first. And so after Curve proves the uniformization, he was interested in the following. So suppose sigma is a genus 0 Riemann surface. Okay, it could be non-compact, and then it's known that this Riemann surface is biholomorphic to an open set in the complex plane. So in case it's simply connected, non-compact, then so non-compact, let's say. So Curve was interested in, so if it's simply connected, it's going to be C or the D. But what about if it's not simply connected surface of genus 0? We know it's this open set. Can we sort of make this open set unique in some way so you can see, you can realize these Riemann surfaces in some canonical way? And here is what what Curve proved. His theorem says that any sigma is a genus 0 Riemann surface homotopic to a compact graph. So it's a finite type. So this Riemann surface is a two-sphere, remove a finite number of holes and points. Then sigma is biholomorphic to, it's analytically the same as a C minus x, where x is a finite union of of points, finite disjoint union of points and round closed disks. So every finite type, topologically finite type Riemann surface, it can be uniquely realized as follows. You take a finite set of points and finite set of round closed disks. And you look at the complement of that. Maybe I should put the Riemann sphere. Then it's going to be, these are called the circle domains. Okay, so that's what. So every finite type Riemann surface is a genus 0 is a circle domain. And then he made a conjecture that this should be true for any genus 0 Riemann surfaces. So that's here is Koebe's conjecture. So let me make a definition. A closed set X in the Riemann sphere is of circle type if every connected component is either point or round disks. If every connected component of X is a point or a round closed disk. Okay, so the Koebe conjecture, which is still open, says that, so this is the Koebe conjecture. So every genus 0 Riemann surface is biholomorphic to the Riemann sphere minus X, where X is of circle type. Okay, so these are called, Koebe calls these are the circle domains. It's a beautiful conjecture. And the best result at this moment is by John He and Odette Schramm. And the statement is that it's true if, so let me give this a name. So true if sigma has accountable ends. Okay, so this is the same thing as X has countably many connected components. X has accountable components. Okay, so X should contain no Cantor set. If there is a Cantor set, then it's not known. And they also prove a stronger statement that in this case, if the Riemann surface has countable ends, then X in this case, X is unique. So they also prove X unique up to Jungius transformation. Okay, so it looks like, so here is what we see now. The discrete version of uniformization should be a geometric version of this. So here is a conjecture by us. For any complete genus 0 hyperbolic surface, So basically, you take the Riemann surface in curves situation and put the uniformization metric. Generically, it's going to be a hyperbolic metric. Then there exists we conjecture even unique. There exists a unique up to Möbius transformation. Unique circle type closed set X such that this guy is isometric to the boundary of it. So sigma D is isometric to the boundary of the convex hull of X. Okay, so this will really cover more than the discrete uniformization that we hope for. It covers every genus 0 Riemann surfaces. So let me tell you what is known about this. And according to Thurston, by the way, this boundary is always hyperbolic, and so the other way is guaranteed. There's no. So what is known about this conjecture? Well, the first case is if the area of the hyperbolic surface is finite, it's true by the work of Riemann. So Riemann proved a theorem which says that I give you any hyperbolic metric of finite area on a punctured surface. This is a two-sphere with some cusps and a hyperbolic metric. And then you can find, in fact, the unique ideal convex polytope in hyperbolic space whose boundary is isometric to the given one. Okay, so this is like in curves. In some sense, it's a curves situation. If the topology is finite, it's true. And the second case is by Schlenker. He proved that true if your Riemann surface is biholomorphic to a sphere minus a finite disks. So if your Riemann surface has all these whole boundaries, okay. So this is now a infinite area, but and in that case, you can now, it's no longer, the convex hull is no longer convex body, it's some convex surface. And so you can choose some round disk here and round disk here. And you do the convex hull. And you can prove it. And so that's Schlenker's work. And we proved the recent, so it's open, by the way, if you mix the two. If your Riemann surface is either has some finite number of holes and finite number of cusps, that's open. No one knows how to prove it. And we are able to prove recently, so true for, this is a joint work with Tillman and Wu. So true if the surface is has one whole boundary and finite cusps. Okay, so this is the proof is kind of technical, but this is good enough for us in terms of the discrete uniformization. Discrete uniformization really address only two situations, that the Riemann surface is a Riemann sphere minus a discrete set, was a disk minus a discrete set. And that's the situation. That's what we can prove. Okay, so that's that. And let me also tell. So I've been trying to read a lot of these classical work by Alexandrov and Pogorelov, and so in fact they've done a lot of work, amazing work. Except it's sometimes difficult to understand their proof. So let me tell you one more evidence of this coming from Alexandrov's work of this conjecture here. So I mentioned here, Alexandrov proves this. This is sort of the first theorem he proved in this Alexandrov geometry, and then he generalized it to a very general setting. So here is one theorem appeared in his collected paper, volume 2, but there are no proofs. Okay, so there's no written proofs here. So, but I think it's true. I couldn't find the written proof, but it's related to what we are doing here. And so let me tell you, these are sort of the supporting evidence of this conjecture. So here is the Alexandrov theorem. So suppose sigma d is a complete genus 0 path metric space of curvature defined in the path metric sense. This is really, really general, which address all the boundaries of the convex set. They may not be smooth, but they all satisfy this condition. The curvature bigger than or equal to -1. So if this guy is Z, then you can find a closed convex set P in the hyperbolic space such that D is isometric to it. So there are no compactness assumed, okay, and it's definitely the uniqueness is definitely false in this generality. So take any closed convex set in hyperbolic space, look at the boundary, it's going to be a complete genus 0 path metric of curvature minus at least -1. That's convexity. And he proved the other way around is true. So if we take the special case, so the special case, I'm going to take sigma to be the complex plane minus a discrete set, which is what we're interested, and D is equal to the Poincare metric. It's a complete hyperbolic metric in the conformal class of this. Then if you apply this Alexandrov theorem to it, you will see it's going to be the boundary of some convex set, because now the curvature is equal to -1 everywhere. It's constant, and you can show that it's by tiny small work, it's going to be isometric to the boundary of a convex hull of some E prime is a discrete. Let's see. Okay, so constant curvature -1 forces this closed convex set to be the convex hull of a set at infinities, and this guy has cusp-band and forces to be the point. And so in other words, in the discrete conformal setting here, if the underlying complex structure is C, the existence theorems was already proved by Alexandrov, and the uniqueness part is difficult. Okay, I guess I'll stop here. Thank you.